Part two of this video is going to talk about the Big Bang, which we have a bunch of evidence for. So evidence number one is something called redshift, which we'll go on to explain in a moment. Evidence number two is something called CMBR, which again we'll come on to in a little bit. So Big Bang, very, very confident scientific theory. Evidence for it we learn at GCSE. So let's dive in. So redshift is an example of something called the Doppler effect. Now, the Doppler effect doesn't apply to stars or space necessarily, but it can apply to any wave. So let's look at an example. So let's say you're standing in a street and you hear an ambulance drive past you. Now, the ambulance is obviously got its sirens on, it's on its way to emergency, it's emitting sound quite loudly. So you, as you hear the ambulance go away from you, will have a different perception of the sound to someone on the other side of the ambulance. So let's say the sound waves hit you as it goes past you. Someone on the other side of the ambulance, which is travelling towards them, the waves are slightly closer together because the ambulance is travelling towards them. Now, as you can see from the diagram, if you compare the wavelengths, if it's travelling away from you, there's a longer wavelength. If it's travelling towards you, it's a shorter wavelength. For sound, a longer wavelength sound means it is a lower pitch or a lower frequency sound, and a shorter wavelength means there's a higher pitch or a higher frequency sound. So that's what the Doppler effect is. Now with redshift, we apply this to distant objects in space. So let's take our two people again. Let's say they're in different parts of the universe, and we've got a galaxy that's emitting a light. Now it's emitting all different parts of the EM spectrum, all different colors, but if it's traveling away from us, it will have, like we talked about, a longer wavelength. So let's look at the colors of the rainbow and see which one's got a longer wavelength. So red, orange, yellow, green, blue, indigo, violet. Hopefully you can see from the diagram that violet and blue has a shorter wavelength and red has a longer wavelength. So as the galaxy travels away from the person or the observer, the wavelength it is giving off is slightly shifted towards the red end of the spectrum, or a longer wavelength. And if it's traveling towards you, it's what's called blue shifted, which means the wavelength has been decreased, so it is more blue shifted. Now, why is this important? Why is this good to know? Well, let's get a definition down for redshift first, and then we'll look at the consequences of what we observe when we look at this. So, how you describe it in an exam is redshift is when light from emitting from a galaxy, so not star, definitely not planets, but galaxies, because they're really far away, that's what we can see, that are moving away from Earth, has a shifted towards the red end of the spectrum. So has shifted towards the red end of the spectrum. Now you could say it's got a longer wavelength here as well. That would be also some extra information to put in, but please don't say it's more red. That doesn't get you marks. It's shifted towards the red end of the spectrum. Now, if we want to talk about something that's blue shifted, obviously you replace red with blue, and that would be something that's moving towards the Earth, and it'd be shifted towards the blue end of the spectrum. Now, we don't talk about blue shift as much because almost all of the galaxies we observe in the night sky, apart from our nearest neighbour, is red shifted. So what that means is if we were to observe all the different colours in a spectrum, now don't worry too much about what a spectrum is, we learned a little about it at A level, but it shows all the different colours, and there are what's called absorption lines. And if these lines have shifted slightly towards the red end, like these ones have, then that shows us that the light from that galaxy is red shifted and it's travelling far, it's moving further away from us. So what do we notice when we look at all these things? Well, we actually notice that almost all those galaxies are redshifted. So actually almost all those galaxies we observe are moving further away from us on planet Earth. So let's look at then if we were to plot a graph of these two things, and this is something that Edwin Hubble did over 100 years ago now, which is to look at the velocity versus the distance they are away from us. So the further away they are they moving faster or slower? Well, actually, if you plotted all the points, there's a fairly positive correlation, and the two things are actually directly proportional because it's a straight line and it goes through the origin. So what that shows us is the further away a galaxy is, the faster it's traveling. So the further distance, the higher the velocity, and that means that it all came from one point, which is the Big Bang. Now, let's have a look at evidence 2, CMBR, which stands for Cosmic Microwave Background Radiation. So cosmic means kind of to do with space. Background is just it's in the background. Radiation is a type of radiation. Now, microwave we should know is part of the electromagnetic spectrum. Now, let me tell you about a little bit how it works. So the analogy I'm going to use is that of a balloon. So a balloon is like space. It's expanding. So if I was to draw a little dot on the balloon or a symbol, if I was to then blow up the balloon, the dot stays the same, but it kind of expands. This is representing space expanding. Now, cosmic microwave background radiation. Radiation is a wave. So if I was to draw a little wave on the balloon, it would expand out to be an even bigger wave with a bigger wavelength. So how we'd go about describing the CMBR is to say that radiation, this is from a long time ago, this is from the Big Bang itself, or the very short seconds after the Big Bang, his wavelength has increased because, or as, the universe has expanded, so has expanded outwards. And this is a big deal because it actually was predicted before it was discovered. So this is a massive evidence for the Big Bang being true, so this radiation has expanded to the microwave region of space. Now, if you were in school in a few billion years' time, if you look at the EM spectrum, currently it's microwave. If it was to expand even more, have a higher wavelength, it would actually